What is crucially important, however, not just for your A levels, but in organic chemistry, is the reaction between the nitrosyl cation and aniline here. Now, of course, aniline, that lone pair on the nitrogen, is very much tied in with the electron cloud, that pi electron cloud in the benzene ring, which, of course, as we've already seen, significantly affects its basicity. It also affects, generally, its reactivity with the nitrosyl cation. So let's take our nitrite in the form of sodium nitrite, put it in with a strong acid, HCl, H2SO4, whatever it might be. Here is our diazonium cation, exactly the same as we saw for the primary amines, but now it's not an alkyl diazonium cation, it's an aryl diazonium cation. Aryl means it's got an aromatic group here. Okay, now these aryl diazonium cations are actually much more stable than the alkyl ones. Now, it's not saying much because you get above 10 degrees Celsius and it decomposes, but as long as you keep it cold, it's relatively stable. Now, the two reasons for that are, of course, because again, we've got a nice pi cloud here, double bond or triple bond here, lots of pi electrons can get all sucked up with the aromatic ring, so they can be delocalized around the ring, making it nice and stable. The second thing is that the reason why the alkyl diazonium cations were really unstable was because this just leaves as N2, leaving you behind with the carbocation. Well, if we lose N2 from this thing, we make this carbocation a positive right on the benzene ring. That's extremely unstable. It's not a very good carbocation at all. So for both of those reasons, first of all, the electrons in that N-N triple bond can all be tied up with the pi electrons in the benzene ring. And then secondly, if they left, you'd have a very unstable intermediate. This species is relatively stable, certainly nice and stable at temperatures, certainly stable enough to do things with it. Now, at A level, you don't mention most of the things you can do with these aryl diazonium cations because they are superb reagents for making all kinds of substituted benzene rings or substituted aromatics generally, because you can lose this N2 and substitute for it quite happily. And here's just a variety of what you can do with it. React it up with water, you make a phenol. Okay, it's one of the main ways to make substituted phenols, because you take a substituted aniline that's got some groups hanging off it, turn it into the diazonium cation, react it up with water to make the phenol. It's the primary way to make both iodo and fluorobenzenes. Iodobenzenes with Ki, fluorobenzenes with this particularly nasty species HBF4 with heat. You know how to put chlorines and bromines on aromatics. However, if you remember, putting chlorines or bromines on makes the benzene ring less reactive. So you kind of want to do it right at the end. So what you can do is you can do the chemistry you need to do, end up with the aniline derivative, turn it into the diazonium cation, and then put either chlorine or bromine on. You can put cyanide on quite happily. And if you want to, you can put it with a weak acid like acetic acid or phosphoric acid and just go back to just having an H there. Doesn't seem much point to do it from this to make benzene, but on the other hand, if you've got all kinds of other strange substitutions on here that you've managed to do, then you can finish off by just putting a hydrogen on. Very versatile, useful synthetic reagent.